Hey guys, I'm back. Alright, here we go. We're working on chapter 23, brazing, braze welding, and soldering. Okay, so here we go. Well, if I can make it go. Alright, so when we talk about brazing, we're really talking about joining two pieces of material. But instead of melting the actual base material, we are only going to melt the filler material. Okay, and usually brazing is above 840 degrees. Okay, so the most common joints that we're going to use are a lap joint and a butt joint. The thing is that the lap joint is actually a lot stronger because if we look, there's a lot more surface for it to connect. Okay, when we look at a butt joint, whether it's a scarfed edge or a flat butt to butt, there's not really a lot for it to stick to. So we tend to kind of stay away from butt joints if we can help it. We want to make sure that we have as much adhesion as possible. But when we braze, it also allows us to use dissimilar materials. Really pretty cool, right? So pretty much when we braze, it's like the glue between two pieces of paper or two pieces of wood. We're not changing anything about the material itself. We're only changing the filler metal. All right, so in order for us to have a good brazed joint, we actually have to have a fairly tight clearance. If we look at this, 0.0, usually the most effective is 0.001 to 0.010, which means we need to make sure it's nice and tight. We don't want it overly tight, but pretty much what we want to do is we want to clamp it down to make sure that it works. Brazing works by capillary action. So let me go back and show you. Capillary action means is that if we keep this joint or this joint here relatively squished down, what will happen is it will actually, when we heat this area up, it'll actually suck through all the way to the other side of the joint. Okay, that would be capillary action. For example, if I got a piece of material off of the saw and it has that water that sticks it together, it makes it very difficult for it to come apart. That's capillary action and the surface tension working with it. Okay, now we're using that with a material that gets hot, so it'll spread everywhere and stick to each other. Okay, pretty cool, right? So these shows us the filler metal group. We know that it's a brazing filler metal by the B in front of it, and then what it does, it gives us the chemical symbol for the material. So aluminum, silicone, copper, silver, gold, zirconium, magnesium, nickel, or excuse me, zinc and nickel. Okay. Now the other thing is that we need flux. Flux helps things stick together, okay? What flux does is it kind of cleans the material to a certain effect. It's not going to get off any grease or dirt or grime, but what it's doing is it's actually taking out what are called oxides and anything that could affect it, okay? It also is corrosive, so it's going to give it a little bit of a tooth for everything to kind of stick on a little bit better, okay? So we have different types of fluxes used for different filler metals and used for particular base metals, okay? So they have to match what we're trying to do. Now, flux can come in many different things. It can come in powders, it can come in pastes, it can come in liquids, and we can even get flux that already is put onto our rods, and that's how we usually do it. But if we're going to use a powder, what happens is that we'll get the rod hot, and then we'll dip it into the powder so it sticks on it, so it's ready for us to go. Pastes and liquid kind of work in that same way. Okay. All right, so here it is to apply a powder flux. Here we go. We're going to heat it up and dip it in there. All right, so AWS classifies materials by the B for brazing: aluminum, silicone, copper, phosphorus, silver, different precious metals. That's gold. Copper, copper, zinc, nickel, magnesium. Okay. So these are all of the things. Here's my brazing metal, and we want to what? Match our filler metal with our base material, okay? And we're going to make sure that we use the same type of thing. Now, when we use the heat, we need to pay attention to how we use the heat. Normally, when we use a gas torch, that's usually how we braze, we're going to use an oxyacetylene welding torch, or there's many different types. We can do MAP gas or butane, but whenever we're doing that, we don't need to use the inner cone. When we weld, we're actually going to use the outer envelope, which means it's not going to get as hot and we're not going to melt our base material. We only want to get it hot enough to melt our filler material. Okay, so here it is, the outer envelope, the outside of it. We don't want to hit the inside when we're doing that. All right, now let's talk about different types of brazing. This gets a little crazy and stuff, but let's talk about it. So this is for something that's going to be like production work. So what they're going to do is they're going to put the assembly together, they're going to put flux on it, they're going to lay the filler metal down, and they're going to clamp it all down, and then they're going to put it through a furnace. Okay, the furnace is going to melt the filler metal and melt the flux, and it's going to flow to where it needs to go. And then as the conveyor belt goes through, it starts to cool it off and solidifies into a brazed joint. Okay, now this one's called induction brazing. What happens is that we have either an electrical coil or a water and oil coil that goes around this area to warm it up. Okay, and here they're going to put the workpiece near it so that it gets warm. The only problem with this is that the heat isn't going to be the same all the way around, so we can have a little bit of an issues with some pieces not being melted fully. Okay, that's the only thing with an induction coil. A lot of induction coils are actually used to preheat like piping and things like that. All right, resistance brazing. Well, we talked about spot welding, where we take two pieces of copper and we put the electricity through it, okay? But this is different. So we're going to put the electricity through it, but we're not putting enough current through here that we're going to melt our base metal. So here's our base metal. We're not going to melt that. We're only putting enough current to melt the filler metal. Now, if we're doing resistance brazing, we know brazing is what? Over 840 degrees. So approximately we need, a few amps here and there to make sure that we don't go over that. That's going to melt our base metal. All right, dip brazing. I think this is the coolest step ever. Okay, so there's different ways that they can do it. They can do it in, getting these little assemblies together. Okay, they're sticking everything together and then they're dipping it into, pretty much the braze material, and it's going to only stick to the areas that have been fluxed. Okay. The other one is that they're going to do like a second, a dip 1 and a dip 2. Kind of like when they chrome parts, they're going to stick it into a material where it sticks to it, and then the other one that's where everything's going to stick to. Okay. The thing is that when we do things like that, usually it's for smaller parts. They do this for electrical boards and things like that when they can do it very quickly. All right, so we're talking about here is, well, what do we do? What's braze welding? Well, here it is. Braze welding. Let me give you the official definition, and that way we get a good idea. Braze welding is a joining process that produces a coalescence of metals with filler metals that begin to melt at temperatures above 840 degrees. The only difference is that braze welding does not use capillary action, which means we do not have to have a tight joint clearance. Okay, and then we can also make it a really pretty bead. Now, when we do this, we need to make sure that we heat our base material efficiently and what they call tin it. That means we're going to put a nice thin coating of our filler metal onto our base metal before we run that nice pretty bead. All right, now here it is. Copper zinc metal is used. So here's all the fillers. Okay, this is for braze welding, RB. Okay, I don't know why they use RB, but braze welding. Okay, it should have been BR, but I think it got confusing. Okay, so here's all of the different things that we see. Chemical composition and the tensile strength. Now, remember, we're going to match our what? What's our number one? Matching our base metal with our filler metal, and we want it as strong or stronger than our base material. We also have to think about it when we're brazing and braze welding, that if this is subjected to high heat or a lot of stress, this might not work very well. Okay, we have to think about this. This isn't as strong as if we would weld it. Okay. All right, so let's talk about soldering. How is soldering different? Well, soldering does not melt our base metal. Oh, come back. Soldering does not melt our base metal, but it also melts at a lower temperature. Anything below 840 degrees means that it's going to be soldered. We're usually using soldering because the base materials are very, how do you say, will melt very easily. Okay, so we're using compositions that will melt very low. So what do they mean by solidus and liquidus? They mean solidus is this will solidify, this will get solid at this degree, and it will get liquidus or liquidy at this degree. On average, solder gets about 471 degrees, give or take, okay? But on average. So if we look at what it is, so this tells us it's what the composition of it, okay, what's in it, and how hot or cold it gets. All right, so usually they have tin, lead, antimony, and silver. Okay, joint designs for soldered seams. Well, they are also determined by what we need the seam to do. Okay, if you notice, a lot of them are lap joints. They call this one the joggle. It means it kind of sticks out a little bit. The grooved, pretty much we're kind of rolling it over and then soldering it. The double, or it just depends on how we're doing it. So we're trying to get as much strength out of this joint as possible, but remember, these materials are usually really ductile, really soft, and they can melt quite easily and are usually deformed really easily. So we can also solder with different things. I don't know if any of you have done soldering before, but can have a soldering copper. I used to use these a lot for larger pieces. An electric soldering iron, we can put very tiny points on this. This is more for electrical work. And then we can also use a propane gas torch. Okay, remember, we're going to silver solder what? Copper. Okay, and we're going to use a gas torch. All right, and here it is. Boy, I'm pretty good at this one, huh? Here it is. So we're soldering copper pipe. We're not brazing it. We need to solder it. Not because that the copper will melt so much. It's that we have better adhesion when we use silver solder. Okay, so there's two different techniques that they talk about. One, this is called a seam solder. Pretty much it's edge to edge, and we're able to see the solder along the outside of it, okay? Now, they call sweat soldering when it's going into the joint with capillary action and we're not seeing any solder being visible, okay? It's going to be stuffed under something like a lap joint. All right, so we want to use the lowest effective brazing temperatures so that we can minimize grain growth, warpage, and hardness. Pretty much when we're using brazing, there's a reason. We don't want to affect the chemical composition or how the material is reacting. Okay, maybe we're using dissimilar materials that aren't going to melt together very well. We use a joint design for brazing based on the adhesive qualities of the filler metal and the joint clearance. We want the smallest joint clearance as possible. Surfaces to be brazed, they need to be clean. They have to have no oil, no grease, no dirt, no oxides. Otherwise, I will guarantee they will not stick, they will come apart. Okay? We also want to use the appropriate filler metal and flux recommended for the metal to be brazed. Okay? That's the filler metal to be brazed and the base metal to be brazed has to be looked at to make sure that everything is jiving together, including the flux. Okay, so we can use oxyacetylene, we can use MAP, but we also want to make sure that we use the outer envelope of the flame, okay? So when we braze and solder, we're using the outer envelope because it's not as hot. When we need to weld, we're going to use the inner cone. We want to make sure that we also remove all of the flux. Remember, I was telling you that flux kind of is a little bit of acidic, and it will actually start to corrode away your material, so we want to make sure that we clean it off well. We want to use a procedure for braze welding, okay? Any type of welding procedure means, or I should say, any type of welding process means we use a procedure. We want to make sure that we clean everything before we apply filler metal. And when we're doing braze welding, we want to make sure things are tinned before we put the bead on. So we're going to put a thin layer of filler metal before we put a nice bead down. A neutral flame is used unless otherwise specified, and we want to kind of go circular motion. Okay. We don't want to braze a material that's going to be subjected to what? High temperatures or high stresses, because we know either of those is just going to let all of that filler metal kind of run out and it's not going to do its job. When we solder, of course, our parts need to be clean, they should be fluxed, and we need to make sure that they fit closely together, because when we solder, the material is a lot, melts a lot quicker, and it will solidify a lot better. So we want to make sure not only do the parts not move, but we have really, really good fit. Okay, we want to wash the soldered work with hot water to eliminate the corrosive action of the flux. And we want to make sure the soldering heat is adequate for the soldering job to be done. Okay. All right, guys, we'll have some questions in just a minute. Take care.